Question 3 is predominantly an equilibrium question. So we've got this equilibrium here, 3.1. So it's hydrogen and iodine in equilibrium with 2 moles of HI. And we're told that the enthalpy change for the forward reaction is minus 9 kilojoules per mole. So therefore the forward reaction must be exothermic. We've then got to complete this enthalpy profile diagram for the forward reaction, and we've got to include these 3 bullet points here. So the first thing is our reactants obviously go here, so that's the H2 and the I2. Because it's exothermic, our product line must be below in terms of enthalpy, and we've got 2 HIs sitting on that line there. The 2 lines are connected with this curve, and then the activation energy is the energy we have to raise the reactants to, so that's an upwards arrow, not a double-headed arrow, an upwards arrow from this line here to the top of the curve. And the enthalpy change is the difference in enthalpy of the reactants compared to products. So that's a downwards arrow in this case, and again it's a single-headed arrow, not a double-headed arrow. The activation energy for the reverse reaction, so if you imagine you were starting here, that was your reactant and you were making these products, and obviously you've got to climb up to there first, so that's going to be 9 kilojoules per mole, and then you add on that 173, so that's 182. Gets a bit tricky now. When the reverse reaction takes place, hydrogen iodide decomposes to form iodine and hydrogen. Calculate the enthalpy change when 336 decimeters cubed of hydrogen iodide measured at RTP decomposes. And we've got to include the enthalpy sign in the answer. So the first thing I will be doing is, they've given me a volume of a gas, so straight away you can work out how many moles that is. So that comes out at 14 moles. 336 divided by 24 dm cubed is 14 moles. So we need to know what the enthalpy change is for 14 moles that are decomposing. The enthalpy change for the reverse reaction would be plus 9 kilojoules per mole, going that way, and that's for the decomposition of 2 moles. And so therefore we need to find out, well, we want to know what 14 moles would do, and so therefore it's 7 times this, and so 7 times plus 9 is plus 63. Part D is just a little bit of recall from your knowledge of dynamic equilibria. So apart from the closed system condition, another feature of a dynamic equilibrium, well, you could say that the rate of the forward reaction must be the same as the rate of the reverse reaction, or you could say that the concentrations of everything remain constant. So the student heats the equilibrium mixture, keeping the volume constant. Predict how the composition of the equilibrium mixture will change. Explain your answer. So we know that the forward reaction is exothermic. So if the student heats this further, then it will favour the reverse direction, the endothermic direction, and so it's going to move in the reverse direction, and therefore what's going to happen to the composition of the equilibrium mixture? Well, the H2 and I2 would increase and the HI would decrease. Part 3, predict and explain what effect, if any, an increase on the pressure would have on the equilibrium position. And so what do we need to look at now? We need to look at how many moles we've got each side of the reversible arrows. And we've got 1 and 1, 2 moles of gas on the left, 2 moles of gas on the right. So pressure will not alter the position of this equilibrium. And so there'll be no effect on the position. Why? We've got the same number of moles of gas on each side. And then the final part of the question is the bond enthalpy part. Calculate the bond enthalpy for the HI bond in equilibrium 3.1 given the following data. Remember, we know the delta H for this reaction is -9. So you can see I've drawn out the equation sort of in a sort of displayed way. So we've got an HH bond and an II bond, and that's going to form two HI bonds, and the enthalpy change is -9. And so the energy in is going to be the breaking of 1 mole of HH, so that's 436, and we need to also break the II bond, which is 151, so that comes out at a total of 587. The energy that comes out is what we need to find out, so we're going to get two HI bonds formed, and the enthalpy change is -9. And so the way I sort of explain this is the delta H is equal to the energy that goes in minus the energy that comes out. And so we plug the numbers in. We've got 587 plus our two unknowns, and that equals -9. And we rearrange to get the two unknowns on their own. So it rearranges to this. And then we divide by 2 to get the bond enthalpy for one HI bond, and it comes out as 298. And remember, bond enthalpies always have positive signs. If you're getting a negative answer there, that's not right, because you've always got to put energy in to break bonds.